excuse me, it's going to get recorded, so please don't do that.
Vale.
Right, so we are back in, and I finished grading the first midterm for this class. It took me a while because it does take a lot of time, especially for question 4, to scan through the whole thing. When you look at your grade, it will be in the form of homework assignments, but it's not really a homework assignment. There's nothing to turn in, but that's what it will look like. You will get a score, and if you click on the quote-unquote assignment, you will also see how it's graded. It's basically rubric-based. And on each item, I will select one of the grades for one particular aspect of your answer. Yep.
I have a question about the grading scale. Because the rubrics, it looks like there's way more points in there than it says on the test itself.
That is correct. It is scaled to the number of points in the for that question.
Okay,
Yeah.
that's what I thought.
Yeah, so it's also going to be scaled, and then when you add up all the points from the exam, that should add up to 20 points, which is the 20% of the first midterm.
Is it 20 points or 25?
20 should be 20. If it's 25, it's going to be scaled to 20% of the final grade. All right. So, are there any questions regarding the first exam?
So the grade total, the accumulation of those 4 questions,
Right.
that grade is our actual grade for the whole.
For exam 1.
Okay.
For the entire exam.
Yeah, that's on the whole
Yeah.
of the
Yeah.
exam.
So for this class, I finished all 4 questions. So what you're seeing should be what you're getting for that exam. I'm still in the process of grading the 1030 class, so they won't be seeing the entire grade. They'll be seeing only the questions that I have graded up to that point, up to this point. All right. And I prepared new row sheets today. And let's see, this is for this class. So if you see more than like 3 bars next to your name, that means you have more absences than you should. And I need an explanation of some kind, okay, if that is happening to you. There's only one person in the class with 4 bars, so when I pass the row sheet, you guys can take a look at it and make sure that I did not miscount anything.
3 bars, okay? 3 bars?
3 bar is borderline. Yep. You don't want to get any more than 3 bars. I was quote unquote cleaning up my roster this morning, so people with 5 bars, gone. Because it's 6% of your total, attendance. So 6% adds up to what? We did this at the earlier part of this class.
Mm-hmm.
We have 54 hours for this class, of all the total meeting time. So let's do some calculations.
54 hours. 10%, 5
All right. So we have 54 hours as the total amount of meeting time, and you multiply that by 60. We have this many minutes to meet per semester, and you multiply this by 6%, which is 0.06. This is the number of hours that people can miss. Each class is 80 minutes, so if you divide it by 80, that is 2.43 classes. So that's why 3 is a magic number, because 3 classes will add up to 240 minutes. Which is just a little bit more than 6%, but I'm going to count round it up to exactly 3 absences. So that's why people with 3 absences are really right at the threshold. Any more than 3 would be more than 6%, definitely more than 6%, and that's eligible to get dropped because of excessive absences. Yep.
What about if it's an excused absence?
If it is excused, it is okay. If it's a sickness, I need doctor's note if it is more than just once, because that's what I need for the absences. All right. Okay. So now that we have that out of the way, let me make sure this is the right class. It is the right class. Some people might notice that this Moodle has changed a little bit. The style has changed. That's because I changed the theme. This particular theme will work on a mobile device. So if anyone has tried to use a mobile device like a smartphone to log into Moodle, you will find that this particular theme is very friendly to smaller screens. You can actually access all the items on the smaller screen as well using this particular style. All right. I'm smelling some organic solvent.
Hand sanitizer.
Hand sanitizer, okay. Yeah, well, I can smell it from here, so that's why I'm just want to bring it up. It's like, what is it? All right, so we are actually past topic 5 right now, but the homework assignment is in topic 5. It is called Array 1. So that's your current homework assignment. You have 1 week to work on it. It doesn't involve any concepts that we have not talked about, so you guys should be able to get started on that one. If you have any questions about Array 1, bring those questions to me next Tuesday. It is due on next Thursday. When is spring break for us?
14th.
14th, okay. All right, so that's your homework assignment. It is it's now assigned. So you'll get started on this one as soon as you can, so that you don't have to worry about it later. We are now currently in topic 6. Now topic 6 is an extension of topic 5. So you got to make sure that you're okay with the material in topic 5 first before you move on to topic 6. The first thing topic 6 talks about is called short-circuited Boolean operators. So we'll start with that one, and then we'll continue with searching in a sorted array, which is kind of interesting in many, many ways. Right, so this is the one that we'll start with at this point. It's called short-circuited evaluation. And it has to do with a statement like this. Okay, if we just kind of focus on the expression, actually the highlighting makes it harder to read. All right, so let's take a look at this one. The little TP symbol or the inverted V symbol here means conjunction. It means and. Okay, we talked about it at the very beginning of this semester. I'm pretty sure some people have forgotten about it already because I typically just spell out and, but occasionally I choose to use that particular notation. So the question now is it actually commutable? It's like multiplication. With multiplication, A times B is the same thing as B times A. When you look at the truth table of A and B, well, it should be commutable. You should be able to express the expression as B and A, and it should still work. But the question now is, well, it doesn't really work in computer programming because some code depends on the ordering inside the conjunction in order to make it work. Okay, so instead of just reading the notes here, I'm going to give you an example. So we'll use examples to illustrate why it is working or why it's not working in some cases when you reverse the order. So we'll go to LibreOffice, go to Calc, and I'm going to use an example that we have seen already with searching, algorithm searching. Well, an algorithm to search for an item, a value in an array, and then we'll use that to illustrate why it is not commutable. This is something that we started to talk about on Tuesday this week, 2 days ago, but I'm going to bring it up again, just basically redo the entire example because I think most people would have forgotten about this one already. Okay, so in this case, we have, I have to go to the tools again and reset all the autocorrect option. This is a huge inconvenience as far as I'm concerned. So I have to go to I also, because it automatically converts lowercase I to uppercase I. And I like to use I as the name of a variable in this case. So I got to change that. Let's see. There we go, much better. So I get 0. And what we want to do is to search for a particular value in K in a particular array. And the algorithm goes like this, while I'm going to do it in the wrong way first, and then we'll do it in the right way. So we'll say, while A bracket I does not equal to the value that we're looking for, which is in K, and I is less than bar A bar, do the following. And inside the loop, we just want to add 1 to I for each iteration, and that's it. At the end of this, we can even indicate the result of whether something is found or not. So found as a variable is going to get the value of I is less than bar a bar. Okay. So this is our pseudocode, and we'll go through a few iterations to see whether it works or not, or in what cases it works, and in what other cases it does not work. Right? We'll fix all this stuff here. And use a separate sheet for tracing it. All right, so when we trace this, we need, a column for comments because we do have a pretty long condition to evaluate. It has a conjunction in it. We have line number. We have our, variable I for controlling which array element we are looking at for each iteration. We have variable k which appears here, but I'm going to give it a particular value. The reason why I set it up like this is so that I can keep the same algorithm when I search for a different item in the array. And then on top of this, we also have array A. And for this particular example, we can make array A fairly short, so we'll only have 3 elements in the array. The way I identify this array only has 3 elements is that I will merge those 3 cells together to basically visually indicate that the array A only has 3 particular items, bracket 0, bracket 1, and bracket 2. And we'll have to initialize these things first because we need to we need the array to have initialized values in order to find a value in the array. So we can put whatever value we want in there. 8, 10, and 5 is fine. For this particular case, let's just say that we're looking for the value 10, which is in the array. So we want to go through one case of being able to find the value that we are searching for successfully, and then we'll try another one where the value that we are looking for does not exist in the array.
We also need to have found on here too.
Oh, that's right, we do. And we can put found over here because we don't need to use it until much later. So we'll put it over here just in case we don't have enough space. We can kind of save space that way, right? Because comments does take up more room in this case. So we'll see whether that's enough space or not. This is our precondition. Are there any questions about how the precondition is set up? No questions? All right. So if there are no questions about how the precondition is set up, we'll go ahead and get started with the algorithm. On line 1, I gets initialized to 0. On line 2, we have a condition to evaluate, and this time it's kind of big, kind of long. A bracket I is A bracket 0 because I has a value of 0 at this point. And A bracket 0, according to the trace, it is in column E, it has a value of 8.
Can you make that larger?
Which one?
The right side.
The trace itself?
No, the size.
The left-hand side, the other right?
No, the right-hand side of your screen.
Oh,
Yeah, the
okay.
trace.
Yeah, the trace.
The trace?
Yeah.
Sorry. Well, that's what I said. That's why I asked the trace.
Oh.
He said no. Okay, so A bracket I is A bracket 0 because I has a value of 0 at this point, and that has a value of 8 at this point. So we are comparing 8 to K, which is, which has a value of 10. 8 is different from 10 is
This is true.
true, okay? So we look at the other part of the conjunction, which is I is less than bar A bar. I, it has a value of 0 at this point. Bar A bar is my notation of the number of elements in the array, which is 3 in this case. 0 is less than 3 is also true. So we have true, and the result is just true, okay? No big deal. So we go into the loop, on line 3. Line 3 is really simple. All it wants to do is to increment I from 0 to 1 in this case. Then we go back to line 2. When we get back onto line 2, even though it is still comparing A bracket I to K, but because I has changed, it is now comparing a different element to K. I is now 1, so A bracket I is referring to A bracket 1, and A bracket 1 is in column F. It has a value of 10. 10 is on the left-hand side of the comparison. K also has a value of 10. 10 is different from 10 is false, okay? So a bracket I does not equal to k is false. What about I is less than bar a bar?
True.
That part is true. So now we have false and true, which is false. So we get out of the loop. When we get out of the loop, we end up on line 5 because we do have one assignment statement right after the loop. So this statement on line 5 is an assignment statement. With any type of assignment statement, you evaluate the right-hand side, the expression on the right-hand side. It gives you a value, and then you store that value into the variable specified on the left-hand side. In this case, the right-hand side expression is I is less than bar a bar. I has a value of 1, bar a bar is 3, 1 is less than 3 is true. So true is the value on the right-hand side, and that's what we're going to store into found. In other words, when we update found here, it is simply saying true. Okay, it's perfectly okay. Do we have any questions about this step? Yep.
What does found mean exactly?
Found means whether that value is found or not.
Oh, okay.
So in this case, it is true. We just found the value that we were searching for. The reason why I use k, for that variable instead of j, is k stands for key. So that's the key that I'm looking for. The key of the search algorithm.
The
Yeah.
I, you refer to the
I
last,
stands for index.
Yeah, you refer to the last procedure you went through, the value of it.
Say again?
For the when it's asking I less than.
It's
or
whatever
equal.
I is that we use in the algorithm. So it is the same I that we used previously. Okay.
That's what I was asking.
Okay. All right.
So if found is false, then F?
Correct. Yep. Well, you can spell out false if you want to. Do we have any questions about this particular trace? Seems to work, right? Okay. So the next question is, what if I'm trying to search for something that is not in the array? I'm going to use another sheet, to trace this one. So in this case, I'm going to initialize k a little bit differently. I'm looking for the value 9, which is not in the array. So I'm going to erase the rest of the trace so that we can start from scratch again. Okay. So this time, we still have to go through line 1. Okay, line 1 still does the same thing as last time. I gets initialized to 0. Because we want to start from the beginning of the array. We are basically looking at or examining each element one by one until we get to the end, or until we find the element or the value that we are searching for. On line 2, we have that condition, which is a bracket I does not equal to k. In this case, a bracket I is a bracket 0 because I has a value of 0. The value of the array element is 8. We're comparing a to k, which is 9 in this case. 8 is different from 9 is true. Okay. And then we have to evaluate the other side, which is I is less than bar a bar. That is true as well because 0 is less than 3. True and true is true. We go to line 3. We add 1 to I goes from 0 to 1. We go back to line 2. This time a bracket I refers to a bracket 1, which has a value of 10. 10 is different from k, which is 9, is also true. I is 1. 1 is less than bar a bar, which is 3. Is also true. We have true, and that is true. We go to line 3, we add 1 to I goes from 1 to 2, we get back onto line 2. So this time a bracket I refers to a bracket 2, which has a value of 5. 5 is different from k, which has a value of 9, is true. I is 2, 2 is less than 3, is true, and true is once again true. We go back to line 3 adds 1 to I goes from 2 to 3, and then we go back to line 2, and this time we have a problem because a bracket I does not exist. Okay, right now we have a problem because the array only has a bracket 0, a bracket 1, and a bracket 2. There's no such thing as a bracket 3 in the array because a bracket 3 would be referring to the 4th element in the array, but the array only has 3 elements. So we have a problem now. Okay. So the first question, okay, there are a few questions that we have to ask here. The first question is, if I did write a program like this, what would the program do in this case?
It probably would give an error because it's looking for something that's not there.
Correct. Well, it depends on the programming language. Okay, so depending on the programming language, the behavior of the program will be slightly different. There are 3 possible choices that I know of. First, you're dealing with C and C++, okay, which is what most of you have to deal with in the next class, which is cisp300. So in that class, because you're using C and C++, what it would do is it would look at the column found, column H, and say that, well, since array A starts in column E, column F, column G, so the next one has to be column H. So it would actually consider column H as A bracket 3 and compare that value, which is currently unknown, to 9, okay? Which is definitely not the right thing to do, because the question mark in column H, let me just kind of point out what it is. So this question mark here in column H is basically saying we don't know what that column is storing at this point. So if it coincidentally is a 9 or can be interpreted as a 9, then the algorithm would accidentally think that, oh, we just found the value that we are searching for. Yep.
If we switch I is less than A bar A to be the first part of the thing, would that stop it from doing that? Because it would get a false immediately?
Only if we have short-circuited evaluation, and that's the whole point of why we have short-circuited evaluation. So that's a good point, okay? But that's kind of where I'm trying to get to at this point. So if I just keep the code the way it is on line 2 in C, C++, it would actually do a comparison to a location that is not really a part of the array. Okay, that's definitely not what you wanted to do, right? Okay, so that's the first option. Second option, we have, let's say, Visual Basic. In Visual Basic, it would actually come back with an error on the screen and say that you're trying to access an array out of bound, on line 2, which is really one of the best things to do, is to basically report it as an error, tell you which line it is, and stop the program right away, because we really should not continue execution at this point. The third choice applies to scripting languages like PHP, Python, Perl, and so on. So in those languages, when you refer to an element in an array that does not exist yet, the scripting language will make it exist. Because it will basically say, oh, I see that you're trying to refer to A bracket 3, which does not exist at this point. The programming environment will make the array large enough so that A bracket 3 does exist. And then it will have an initial value of something that is, well, it's not unknown, but it's an initial value. Yep.
I was just going to ask kind of a quick question about, in Python at least, is array behavior coming in a list? Because list would actually throw an index error.
It does?
Yeah.
So it doesn't extend the list, because you're trying to refer to an item that still does not exist?
At least not on 2.7.5, yeah.
Okay, but in Perl and PHP, I know for sure that it will make it exist. So, yep, so your array, now is dynamically resized to actually have that item. So by the time you compare, I to bar A bar, guess what? Bar A bar is now 4, and because I is only 3, so it would keep going. This becomes an endless loop, and it would chew up memory, because it would just keep trying to make the array larger and larger in those particular languages. Yep. So I was mistaken. I thought Python would do the same thing as Perl and PHP, and it does not. Okay. All right. But at any rate, it's not a good situation to be in. So at this point, if you are tracing a program like this and you're trying to access an item out of bound, out of the size of the array, you should stop right away and explain that you cannot go on because you're trying to access an item out of bound. Okay.
So just put out of bound?
Yeah, you just say, we're A bracket I, which is A bracket 3, does not exist in the array. That's all you need to do is to explain why you have to stop the tracing of the algorithm at this point. Okay. All right. Well, now that we know the algorithm does not work, how do we fix it? There are 2 ways to fix it. It depends on whether the programming language that you're using supports short-circuited evaluation or not. Okay. Almost every programming language that I know of, support short-circuited evaluation, but let's say it does not. Okay. Short-circuited evaluation simply means that in the conjunction, it always evaluates from left to right. And as soon as it has an answer to the entire conjunction, it will stop evaluation. It does not go any further than it has to. Is that making any sense? Okay, no? Okay, so let's deal with that later. But for now, let's think about what if there's no short circuited evaluation. It always it always evaluates both sides of the conjunction. In that case, the solution to fix this problem is going to be a little bit cumbersome, because what we'll have to do in that case is we will keep I at 0, starting from the beginning, and in this case, we'll initialize found to false. In other words, we are assuming that the value that we are looking for is not in the array until it is proven otherwise. Okay, so found is going to be useful in this case. So in that case, in the loop here, then we have the same condition here. We then will specify if not found and I is less than bar a bar, then we'll continue with the loop. Because
For the last one that you did, the limitation that's within the array, where anything beyond 2 with A is not possible.
correct.
The limitations are they made by the trace that you did, or is the limitation within the algorithm?
It has to do with that particular test case because I initialized an array with only 3 elements. But when I try to access, A bracket 3, it is referring to the 4th element, which does not exist.
Gotcha.
Yep. Okay, so in this case, we have 2 things to do. We have found equals to A bracket I equals to K, and then I gets I plus 1, and while. So the loop is a little bit different. I'm showing both algorithms side by side just so that you guys can compare the two and say, oh, okay, so this is how it looks like when we have to fix the problem without the use of short-circuited evaluation. So when you look at these 2 algorithms, this is the problematic one. Okay, this is the one that we have a problem with. And to fix that problem without using short-circuited evaluation, we have to turn it into something like this. We pre-initialize the variable found to false, basically saying, I'm assuming the element or the value that I'm searching for does not exist in the array until it's proven otherwise. So we'll make use of the variable found in the condition of the while and basically say, as long as what I'm trying to search for is not found and the index I is less than bar a bar, which means it is still valid, we'll go ahead and compare first in the array. So the first statement inside the loop is to basically say, okay, let's check whether this current element that I'm looking at, does it have the value that we are searching for? If so, great, we'll store true into found. If not, we'll store false into found. And then we add up, and we add 1 to I to move on to the next element. So when we get back into onto line 3, if we did find the value that we were searching for, then found would be true, not found would be false. Then we have false and whatever, it doesn't matter whether I is less than bar a bar or not, because false and whatever is going to be false. Then we'll get out of the loop.
Can we trace this one using
Absolutely.
the same?
Yep, same test case.
Yeah.
Yep, definitely. All right, so we'll definitely do that. Let's see here. We will switch to the new algorithm on the left-hand side, and then on the right-hand side, we'll go back and copy and paste the test case that we had earlier. So we'll copy and paste this one to sheet 5 in this case. And then we have to get rid of the initial stuff because we are basically starting from scratch again. Okay, so this will give you a pretty good compare and contrast between the 2 algorithms. So this is the second algorithm, the one that has that problem fixed. Line 1 still does the same thing, initializing I to 0, but now we have a line 2 to initialize found to false. Okay, oops, false, there we go. And I still cannot, I'm gonna make it a little bit smaller. I know you guys want it to be a little bit bigger, but I really want to show found also in this case, so I'm gonna have to make it this size. I think sometimes the Dollar Tree has inexpensive binoculars, so that might be helpful in the class, like an opera binocular thing. All right, so we move on to line 3. So this time on line 3, the first thing we evaluate is not found. Found is false. Not false is true. Is that making any sense? Okay. So the first part is true, and then the second part is I is less than bar A bar. I has a value of 0. Bar A bar is the number of elements in A, which is 3. 0 is less than 3 is true. So now we have true, and the whole thing is true. Now, since the condition of a while loop is true, we go into the body of the while loop starting on line 4. Line 4 is reevaluating whether A bracket I does equal to K or not. I is 0, A bracket I has a value of 8. 8 equals to 10 is false. So we are quote unquote updating found to a new value of false. When you're tracing something like this, you have to indicate that it is getting a new value, a new quote unquote new value of false, because I need to know what that line is doing to the variable. It's updating it even though it's to the same value as what it has already. Line 5 is just adding 1 to I. I goes from 0 to 1. Then we go back to line 3. Once again, found is false, not found is true. I is 1 in this case. I is less than 3 is true. We have true and true, which is also true. Then we move on to line 4 again. On line 4, once again, we are comparing on the right-hand side A bracket I to K. A bracket I is A bracket 1 because I has a value of 1, which has a value of 10. A bracket 1 is 10. K is also 10. 10 equals to 10 is true. So now found is updated to a value of true. We go to line 5 anyway, and we add 1 to I. I goes from 1 to 2. We go back to line 3. This time, when you look at found, is true, not found is false. But remember, we don't have short-circuited evaluation, so we do evaluate the second part anyway. So the second part is always harmless to evaluate, because we are just comparing I, which is now 2, to bar A bar, which is 3. 2 is less than 3 is still true. So this time we have false and true, which is false. So we get out of the loop, get to post, and found still has the right conclusion. The value that we were searching for is in the array. So this algorithm does work. Okay, if you look at found as the answer to the entire thing, it still reflects the correct answer and say that, yep, we found what we were searching for. Not a problem. So are we doing okay so far with this solution? Yep.
I have a question. When you find found false, can you explain again? Not found is false, not found is true.
If found, okay, the whole thing has to do with negation. Not true is false, not false is true. So when found has a value of true, not found is going to be false. Not true is false. So that's why we can get out of the loop. All right. So let's test the same algorithm, but with our second test case where what we were searching for was not in the array. Okay, because we want to see, that's the one that broke the original algorithm. So we want to make sure that this algorithm does not get broken because of that particular test case. So we'll go ahead and do the same thing. This time we'll have a sheet 6 doing that, and we'll copy everything from sheet 3, which is the case where we have problems. So copy and paste. There we go. And then we'll get rid of the value, so we can start to trace from the beginning. All right. Are there any questions at this point? We are basically doing the same we are executing the same algorithm, except this particular test case has K being 9 to begin with instead of 10 to begin with. Yep.
Would it change the whole thing if you had a bracket 3? I mean a bracket 3?
It depends on the value of A bracket 3 if you do have an A bracket 3. But A bracket 3 will have to take up column H, and then we have to move found into the next one. Because all elements in an array, they have to be contiguous. They have to be right next to each other.
Yeah.
Yep.
But I mean, if we did that,
Then it will take longer to get out.
because it would be bar A bar would be value 4.
Bar A bar would be 4 because we have 4 elements in the array. All right, so let's go ahead and give this one a spin and see what happens, because last time, this particular test case broke the algorithm, and we'll see whether this one will break the new algorithm or not. I gets initialized to 0, found gets initialized to false, and then on line 3, we have not found, this is true, because found is false, not false is true. And I is 0, 0 is less than 3 is also true, true and true is true. Yep.
Why is there not like one for bar A bar?
Say again?
Like, why isn't there something that indicates bar A bar would be 4? I mean 3, for example.
Because bar A bar means the number of elements in the array.
But it doesn't need to be on the trace. It wouldn't need to be on the trace to indicate,
You just
pretty
count,
obvious
you
that-
have to count the number of elements in array A to evaluate what is bar A bar.
But like, let's say there was 100 of them,
Then bar A bar would be 100.
but you would have to count.
Yes. You have to look at the array A in the trace and find out how many elements it has. Okay, so on line 4, we compare A bracket I, which is A bracket 0, because I has a value of 0 to begin with. A bracket 0 equals K is false. So we update found to false again. We go to line 5, we add 1 to I, we go back to line 3. Found is false, not found is true. I is 1, and I is less than 1 is less than 3 is true, true and true is true. We go to line 4, this time we compare A bracket 1, which has a value of 10, to K, which has a value of 9. 10 equals 9 is false. Found is updated to a value of false. We go to line 5, we add 1 to I goes from 1 to 2, we go back to line 3. Found is false, not found is true. I is 2 at this point, 2 is less than bar A bar, which is 3 is true. True and true is true. We go to line 4. Line 4 is going to compare A bracket 2 this time, which has a value of 5, to K, which has a value of 9. 5 equals 9 is false. We go to line 5, we add 1 to I goes from 2 to 3, and then we go back to line 3. This was how we broke the previous algorithm, okay? Because when I got to 3 and we have not found the element, the comparison of an element to K in the while condition itself broke the algorithm. But this time there's nothing to break, because if you look at the condition of line 3, do we have any square brackets in it? Nope. There are no square brackets on line 3 or the condition of the while loop. So we cannot possibly break the program on that line anymore.
What do you mean
Okay?
by square brackets again?
Square bracket is the indexing operator.
Oh, that's right.
Okay, so now we go back to line 3. We ask the question, what is not found? Found is false, not found is true. No problem, just like before. And this time we're comparing I, which has a value of 3, to bar A bar, which is also 3. 3 is less than 3 is false. Okay, is that a problem? I mean, can we compare 3 to 3? Yeah, that's not a problem. As long as I'm not indexing, using it to index into array A, there's no problem. So this condition is now false because it is true and false. Not found is true, but 3 is less than 3 is false. We have true and false. So the condition becomes false. We get out of the loop, we get to post, and guess what? Found has the right answer. We could not find the value that we were searching for in the array. So the algorithm works without having the problem that we had before. But it's kind of cumbersome because we have to kind of keep updating found all the time in this particular algorithm. Are there any questions about this algorithm and the traces that we have done with it? Go
Is there
ahead.
an instance where found is false can be true?
What? Say again?
Is there an instance if it's given to you that found is false, can it be true in the end?
If found is false,
Yeah.
then not found is true. The previous trace, already has what I think what you were looking for. See, in the previous trace, it turned true. Yeah.
Okay.
Okay. So you gotta stay with us. Okay? You gotta stay with us. Alright. So this works, but it's cumbersome. So the best solution is not to use an intermediate variable like found to get around the problem. The best solution is to use a feature called short-circuited evaluation, or otherwise called lazy evaluation. Okay, it's also called lazy evaluation, and the way it works is like this. Okay, so I'm going to use the next sheet to write the algorithm. So sheet 7 is going to be the new algorithm. The new algorithm goes like this. I is 0, just like before, and we'll have almost the same condition as the one that did not work, except we flip the order between the two operands or the two sides of the conjunction. So this time we compare I first to bar A bar. So we basically say, well, if I is less than bar A bar, which means it is a valid index into the array, let's go ahead and compare also whether A bracket I equals to the value that we are searching for or not. So we just flip the order. And if it does not, okay, if I is less than bar A bar and oops, sorry, my bad here, as long as it is different, not the same, as long as they're not the same, then we are going to increment I, which means, let's look at the next one and see whether the next one is a match or not. Okay.
Well, you say don't matter if you switch them, so it's like, don't matter if you switch.
Well, with short-circuited evaluation, then it matters. That's the whole point of what we're trying to do here. All right. So let's go ahead and trace this one and see what it does. We'll use exactly the same test cases on this one, just like with the previous one. So this way you can compare and contrast the two algorithms. All right. So now we have the traces here. And we go back to the first case where it should be found, and we'll see how the new algorithm is going to do it. Yep, go ahead.
Did you send her the roll sheet? I know you talked about it.
I'm going to pass it right now. Just hold on 1 second. So we'll get rid of this. And the new row sheet for this class is right here. All right, so with this one, it's almost the same as the first one, the one that had a problem. We initialize, on line 1, I gets initialized to 0. On line 2, we evaluate the conjunction. But remember, this time we are using short-circuited evaluation, which means we evaluate the conjunction always from left to right. But as soon as we have a conclusion for the conjunction, we stop and we just say that, okay, we don't have to evaluate any further. Okay? So the first condition that we are evaluating here, or the first comparison, is I is less than bar A bar. I is 0, bar A bar is 3, 0 is less than 3 is true. Okay? So if the left-hand side of a conjunction is true, can we make a conclusion right now and say, oh, the whole conjunction has to be this? No, we cannot make any conclusion just yet. So we do have to evaluate the other side. And then the other side is basically saying, okay, well, let's take a look at A bracket I and see whether it is different from K. A bracket I is A bracket 0, which has a value of 8. K has a value of 10. 8 is different from 10 is true. So now we have true and true, which is true. Okay. So now we move on to line 3. Line 3 is just adding 1 to I. I goes from 0 to 1. And then we go back to line 2. All right. I is 1. Bar A bar is 3. 1 is less than 3 is true. Can we make a conclusion right now? No. So now we evaluate A bracket I is different from K. I is 1. A bracket 1 has a value of 10. 10 is different from 10 is false. Can we, so the entire conjunction is what? False, because we have true and false in this case. So we get out of the loop because of this. We get to line 5. Line 5 is just saying, okay, is I less than bar A bar? Yep. I has a value of 1. 1 is less than 3 is true. So we make a conclusion that we did find the value that we were searching for, and get to post, it got the right conclusion. Are there any questions with this particular trace? It's not any different from the trace of the very first algorithm. Yep.
Why is it considered lazy?
It's not, well, we haven't got to the lazy part yet. The next one we get to the lazy part. The lazy part actually will save us from the problem that we had earlier. Okay? So now we get to sheet 9. Sheet 9 is going to be the one that we had a problem with before. So let's see, where
So the-
probably from here. Sorry, go ahead.
So the short circuit's gonna show that I is less than A bar A is false, gets us out of the loop, and then found will be false also.
Exactly. So we'll basically get out early by just evaluating one side of the conjunction. But we'll definitely go ahead and trace the entire thing, just starting from the beginning. All right, so in this case, we start with line 1 again. It initializes I to 0. We get to line 2. Basically the same thing for the first, all the iterations will be about the same except for the last one. I is 0. 0 is less than bar. A bar is true. We cannot make a conclusion of the entire conjunction, so we are forced to evaluate the right-hand side. A bracket I is A bracket 0, has a value of 8. 8 is different from 9 is true. We have true and true, so the entire thing is true. We get to line 3, we add 1 to I is now 1. We get back onto line 2. I is now 1. 1 is less than 3 is true. We cannot make a conclusion just yet. A bracket I is A bracket 1. It has a value of 10. 10 is different from K, which is 9, is true. We have true and true again. Yep.
I'm sorry, so the only way it would be false is if one was true and one was false. Because if they're both
At
false,
least
it's
one
still
is
true.
false.
Okay.
Yep.
And if they're both false, wait, at least one is false. If they're both false, that's false also?
Yes.
Okay.
Because if both are false, that means at least one is false also. But using the lazy evaluation method, we'll never know that they're both false. Because as soon as one is false, we say, okay, it is false. So we don't even bother to evaluate the second one. Okay. So on line 3, we add 1 to I becomes 2. We get back onto line 2. I is now 2. 2 is less than 3 is true. We cannot make a conclusion just yet. So we evaluate the other side. A bracket 2 is okay because we do have A bracket 2 here. It has a value of 5. 5 is different from K, which is 9, is true. Once again, we have true and true, which is true. We get to line 3, we add 1 to I goes from 2 to 3. We get back onto line 2, and here's the trick. This is the magic. I is now 3, 3 is less than 3 is false, and we make a conclusion right there. Okay, because when you have a conjunction, if one side of a conjunction is false, the whole thing has to be false. And that's why we can stop right there. So that's how we can save ourselves from the problem that we had earlier. Because we stopped short of evaluating the A bracket I in the same expression.
Then we still move to line 5 though, don't we?
Say again?
Then we still move to line 5?
Yes, we do. Yeah, but I do want to show you that we don't have the same problem as before. Go ahead.
Do we put post after line 5 or?
Yes, that part of the trace does not change because if the expression on line 2 is false, we still have to go to line 5. And this time on line 5, I is less than bar A bar is false because I is 3, bar A bar is 3, 3 is less than 3 is false. And then we can get to post. So it does not really change the flow of the program, but it does change how we evaluate the condition on line 2. And the algorithm still comes up with the correct solution. What we were searching for was not found. Yep.
On, say, line 2, you're doing I is less than,
Bar A bar.
yeah, bar, thank you. And would you mark us wrong if we put true after that and then did the other part of it?
I would, the way I want you guys to represent it is to spell out the condition But as soon as you find something is false, you basically just say that one is false, and you don't bother to evaluate the other part of the conjunction.
Well, I understand that, but I'm talking about earlier in the trace. So it's true and true is
Mhm.
true. So if we put true after each one that we're checking, just for
That will be fine. That will be fine as long as you tell me what is true. That will be fine. Okay, yeah, so the way you said it should be okay. I just don't want to see true and true is true, because then I don't know what exactly is the first true, what is the second true, what are you telling me? But as
Okay.
long as you say, I is less than bar A bar is true, and A bracket I is less than K is also true, then I know what you mean by, okay, this part is true, that part is true, and then the whole thing is true as a result. So that will be fine. Yep. Yep.
Why don't we indicate, for example, on line 7 on the trace?
Row 7 of the trace.
Yeah, the
Uh-huh.
comment section where it says A bracket I, why don't we say A bracket 1 or A?
Because that's not what the expression is telling you.
Oh, because of the.
Because whatever you use in the comments has to match the code on line 2. So line 2 is only using A bracket I, so you can only use A bracket I in that expression. Now, how do I know that I has a value of what at that time? Well, I look at the column I and I know instantly what I should be at that point. Yeah. Well, that's the whole thing about the trace is you can go to any particular row, and then you can reevaluate that row and say, okay, did I make a mistake with the evaluation of that row?
Now, if this is an actual program, you don't put a post. We just keep going, or
Yeah.
if
How
this-
do you keep going?
No, if you in an actual program, if you don't program's tracing it, you don't put the post there.
Correct.
What will happen to the program? You just say error, or
No, the program will terminate. It will stop and come back with an answer.
even if you don't put post on it in the bottom?
Well, post is not in the program itself. It's not in the algorithm itself. It is a way for you to tell me that you are done with the trace. Instead of,
Just-
well, I somehow forgot to finish the whole thing, right? So if you don't say post, then I would assume that, okay, you meant that something, you still have more to go, except you did not do that part. If you say post, you're telling me that I'm done. This is really, really done. All right. So any questions about short-circuited evaluation? No questions? So everybody understand the mechanism of short-circuited evaluation? Go ahead.
How do we know if a programming language or an algorithm is going to function from a short-circuited?
It is part of the language specification.
Okay.
So when you look up the conjunction operator and also the disjunction operator, because with a disjunction, if the left-hand side is true, then you don't have to evaluate the left-hand side. If the left-hand side is true, then you don't evaluate the right-hand side with a disjunction.
Okay.
Because true or whatever is always true. It doesn't matter what the other side is. So that's why short-circuit evaluation works for conjunction as well as disjunction. But the way they work is kind of opposite. With conjunction, if the left-hand side is false, you don't evaluate the right-hand side. With disjunction, if the left-hand side is true, then you don't evaluate the right-hand side. But it is usually part of the language specification. So when you look up, let's say Visual Basic, and you say look up Visual Basic, this AND operator as short-circuited, you will probably find an answer, on the using Google or within the Visual Basic documentation. They should say that. C and C++ is part of the language specification as well. So when you look up the ISO standard and also the ANSI standard for the C++ programming language, it will specify that conjunction and disjunction are short-circuited. Okay, that's a good question. So any other questions related to this part of our discussion? No questions? All right. Yep.
You ever gonna be writing this in like a Word document where it says forget routine, like what we did in the last one?
The pre and post conditions.
Yeah.
Well, we're kind of past that point, but
No, I
when
mean
you,
for this, or is it the same way?
for For the pre and post conditions, you have to kind of take into account of the short-circuited evaluation as well. Yeah, because otherwise, you can end up with a trying to access an array out of bound just like before. All right. So if there are no questions about this part, then what we'll do is we'll continue with our topic here. So we're basically done with short-circuited Boolean operators. And here's a trick question: do we have short-circuited evaluation for the negation operator? Not true is false. Not false is true. It's a trick question. It does not apply.
Huh?
It can only apply to operators that require two sides. Negation only has one side. So you have to evaluate it anyway. So there's nothing you can say because you have to evaluate the only one operand of a not, of a negation. All right, the next topic is searching in a sorted array. And I like really this one too. Because I know you guys are falling asleep because of all the dry and boring discussion of short-circuited evaluation, right? Okay, this one is kind of funny. Ah, come on. I cannot position it right. There we go. So the professor, me, is saying, so you can see the conjunction symbol here. Thus, for any non-deterministic Turing machine M that runs in some polynomial time Pn, we can devise an algorithm that da 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 da. And this guy's thinking,
What the fuck?
man, I just wanted to learn how to program video games. As if, the theoretical stuff is not important in game programming. Yeah, I just thought it was funny because
This is true.
because the other one, the opposite is true. When you're programming games, all the theoretical stuff actually comes in handy. It is actually important. All right, so we are now in topic 6, and we're going to talk about searching in a sorted array. All right, so the first thing I want to do is to kind of give you an idea of how quickly we can search or confirm something is or is not in an array when the array is sorted. Okay, so I'll just ask you and say, what is the world population at this point? 7-point-something billion, right? So let's just say that I have a sorted array sorted by whatever, okay, name, ID, or whatever, that is representing everybody on Earth right now. So that this is a huge array. The array has 7-something billion items. And I'm giving you a particular key and ask you, is this person in the array? Okay, the array has 7-something billion items. It is sorted. So the question is, how many comparisons will you need in order to confirm whatever I gave you does not exist in the array? 1. 7 billion. Hmm? And 1?
7 billion and 1.
7 billion plus 1. Okay. So the number of items plus 1. Yep.
Whatever the square root of 7 billion is.
Whatever the square root of 7 billion is.
Yes.
Okay. Any other guesses? 33.
That seems random.
Huh? 33 comparisons. That's all I need in order to confirm an item does not exist in the sorted array. Yep.
Is it because you're taking like the midpoint and checking if it comes before?
Yep, because I'm using binary search. Yep. Okay. So this is the power of binary search. What if world population doubles again? So it becomes like 14-something billion. I need to add one more comparison. 34 comparisons will confirm that someone does not exist in the array. What if it doubles again? We conquered the solar system, so now we can support 28 billion people. I need 35 comparisons. to confirm that someone does not exist in the array. Okay? Now, do you guys see how powerful this technique is? You can double the size of the array, and I need only one more comparison when the size of the array doubles. Okay? So how does it work? Well, it works like this. You have a huge array, so let's say this is the entire array. It is huge. Okay, so there are 7 billion items here. So what we do is we're not searching from the beginning, we're not searching from the end. We take something right in the middle. Okay? So we compare this to what we are searching for. Okay? There are 3 scenarios that are possible. So let's say those small items are here and large items are down here. This is how I sort the array. So if I make a comparison to this item here, 3 things can happen. Whatever I'm looking for, the key can be less than the value of this item. It can be equal to this item. It can also be greater than this item. Does everybody agree that in a comparison I can have 3 possible outcomes? Less than, equal to, or greater than. Is that okay? Equal to is the lucky one, right? It just so happens, whatever I'm trying to find is right here. Okay, good. But remember, my question is, what if what I'm trying to find, k, does not exist in the array? So now it has to be one or the other. What if k is less than whatever I have here, and the array is already sorted in a non-decreasing order?
All you have to do is check the top half.
Exactly, because the bottom half, every single one here, will also have to be greater than the value that I'm searching for. What if k is greater than the value that I'm looking for? I only need to consider the bottom half. So every time I compare, I can basically, only keep 1/2 of what I had to begin with. Is that making any sense? Because, so how many times do I have to divide 7 billion by 2 until it becomes 1? Okay, so you take 7 billion, you divide it by 2, it becomes 3.5 billion. You take 3.5 billion, you divide it by 2, it becomes 1.7 billion. And you keep doing this until the number is less than 1.
So log base 2 of 7 billion?
Mm-hmm. So it's basically the log of 7 billion divided by the log of 2 in this case, and then you take the ceiling function, which means we're quote unquote rounding it up, so that way this will give you the number of comparisons that we need in order to perform the comparison to the point when we can say, okay, it does not exist. It doesn't matter whether this log is 10 based on base 10, base e or whatever, because as long as the base of this log and the base of this log are the same, it works out just fine. Okay? So what is a quick way to find out what this number is? We have 7 billion and here's 2. How can I come up with 33 just like that? Because Tech, you looked up that number before. No, I did not. There's a quick and easy way to do it. How do you write 7 billion in decimal? It's 7 followed by how many zeros? 9 zeros. Very good. Because it is 7 times 10 to the power of 9. Is that okay? So when you look at binary numbers, 2 to the power of 10 is 1024. And in most cases for guesstimating, 1024 is close to 1,000. Are we doing okay so far? So now I can say that this number is approximately the same as 7 times 1024 to the power of 3. Is that okay? Because 10 to the power of 9 is 1,000 to the power of 3. Okay. So when you look at this number, it becomes 7 times 2 to the power of 10, and then that to the power of 3. Because 1024 is exactly 2 to the power of 10. All right? So, and then with a power and a power on the outside, you can multiply the 2 exponents. So we have 2 to the power of 30. So we only have 7 to deal with now. 7 is closest to which power of 2? Yep. is closest to 8, and 8 is 2 to the power of 3. So now we have 2 to the power of 3 times 2 to the power of 30. And this is a multiplication. You can combine the powers by adding them. So this is basically 2 to the power of 33. So that's a really quick and easy way to do an estimate of, okay, if I want to look at this number as a binary number, which one is closest to this decimal number. It's not exact, but for the purposes of estimation, it usually works really well. All right. Are there any questions about this? Now, with the remaining, let's see here, 15 minutes, 14 minutes or so, I'm not going to give you anything that's technical that I would actually put in a test. But the question is, why is this important? Because if I don't know binary search, I'll probably be using the same search algorithm starting from the beginning and scan all the way to the end. Is that making any sense? If I don't know any better, I would be searching from the beginning. And now, if the array is sorted, I can still have a little bit of a shortcut. Because if the array is already sorted, and if the key, whatever I'm looking for, is, this is the smaller value, these are the larger values. So if the key is greater, let's see, if the key is less than the value that I'm looking here, and everything up to this point do not equal to the key, do I still need to go on anymore? Because all the other values will be greater than the value that I'm searching for, and all the values before do not match it. So I can stop right here. So I can still stop a little bit earlier without using binary search. But on the average, I will still need 3.5 billion comparison until I get to the point where I can exit. So when you compare 3.5 billion to 33, are they off by a little bit? I would say so. Okay? All right. So why is this even important? Well, it is important because even as a game programmer, this can decide whether you keep your job or not. I'll give you, an example using a spreadsheet. Okay.
Does it have to do with efficiency?
Yep.
Because the more lines of code you have, the slower your program is?
Well, it's not the number of lines, it's the number of comparisons or the number of operations that is important in this case. Okay? So let me give you a scenario. Okay, I'm working for a company. The company is downsizing. It's down to me and Pat as the only two remaining programmers or developers in the company. And the company, has to downsize one more time. They can only keep one of us. So it's me versus Pat. Okay? The boss says, I will decide who gets to stay with this company depending on, who wins a programming competition. I'll give you a problem to solve, and whoever can solve the problem the quickest gets to stay with the company. Is that okay? So that doesn't sound too bad. I mean, it sounds like a pretty fair race, but it's not. Because I'm an old timer with the company, I'm still running an old 486 computer because they never upgraded my computer. I never complained, and I'm still running a 486 computer. Pat, on the other hand, joined the company about 3 months ago. So when they bought, Pat, his or her company, I chose Pat because it can be a boy or girl. As per Saturday Night Live, yes. So Pat has a new computer, and that computer has the latest and greatest i7 processor. Okay, so when you think about it, Pat has a very distinct advantage over me. How fast is an i7 processor compared to a 486 computer?
10
Well,
times faster.
I can do a little quick estimate here. Okay, this is also a time to kind of talk about how to estimate the speed difference between generations of computers. Okay, so what I'll do is I'm going to look up 486 as a computer processor. There we go. And the first entry is in Wikipedia. All I need to do is to look up the time frame of that processor. It's a higher performance follow-up of the 386 processor introduced in 1989. Okay, so I'm going to write it down on the whiteboard here. So 1989 was the time when the 486 processor came out, And Pat just joined the company 3 months ago, so I will count it as 2013. Okay? So 2013, this is the 486 computer processor, and this is the latest and greatest i7 processor. So without even having to refer to any Intel documentation or benchmark and stuff like that, I can use the time difference between these two processors to kind of give myself an estimate of how the performance will compare. How many years has passed since 1989 to 2013?
24.
24, which turns out to be a very nice number to have. Okay, so we have 24 years. And according to Moore's law, M-O-O-R-E, Moore's law, the processing speed of a processor will double every 18 months, 1.5 years. Okay, so you divide 24 by 1.5, and that will give us the number of doubling that has happened since '89. Okay, so 24 divided by 1.3 is 16, and that's why I like this number, because it divides nicely into 16. So if you look at 16, you think, well, okay, so Tak's computer is 16 times slower than Pat's computer. That's not really the case, because 16 is how many times it has doubled. So we are not talking about 16, we're talking about 2 to the power of 16. Tak's computer is 65,300. Okay, how about that? Okay, my computer is this. Is this much of the processing speed of Pat's computer. Okay, about 64,000 times slower than Pat's computer. So you might think, well, that means Pat is going to win the competition regardless, right?
Not necessarily.
Not necessarily, okay? Because Pat being overconfident, because Pat looked at my computer, it's like, wow, your computer took like 5 minutes to start up. Mine only took 30 seconds. Okay, there's no comparison. I'm gonna beat you, anyway. So Pat looked up all the algorithms online using Wikipedia and say, oh, linear search is the easy one to implement. Okay, because you can search for algorithms, in Wikipedia too. So I'm gonna look up, linear search. And when you look up linear search, you look up the algorithm, and it should look familiar to us. Okay, this is the linear search algorithm. They use a repeat loop, but it's really representing the same thing. What, 6 lines, right? Okay. But me, on the other hand, knowing that I have a distinct disadvantage to begin with, I looked up the best algorithm for searching, which is binary search. Now, binary search is not nearly quite as simple as linear search because it's a bit longer, okay? And Pat looked at my algorithm, go like, you start off with a very slow machine, and now you want to use an algorithm that's this long? I mean, there's no way you can possibly win, okay? But Pat is forgetting one thing: the amount of time that an algorithm requires to solve a problem is not necessarily proportional to the length of the program itself. Okay? All right. So for the next 7 minutes or so, I'm going to use a spreadsheet to kind of illustrate, how things can be different between the two computers. So here's, me, and here's Pat. Okay, so we're measuring the amount of time in order to solve a problem. And I need one more column, which is bar A bar. That's the size of the array. Okay, my boss is just giving us a problem and say, I'm giving you this array here, and I want you to confirm that an element does not exist. Okay, let's see how long it takes for this computer to get it done. All right. So in this case, let's say the size of the array is 1. There's only one element in the array. My computer will take 1 unit of time to do it. So this one is not any particular unit, it's just 1 unit of time. Now Pat's computer, using linear search, is going to take also one comparison just to confirm that one thing in the array is not what we are searching for. But since Pat's computer is quite a bit faster than mine, Pat's computer is going to take 1 unit of time, but we also have to remember to divide it by 65536, which is 2 to the power of 16. Okay, so this is the numbers so far. This is how much time my computer will take to confirm that one element is not in the array, and Pat's computer will only have to take this much time. Okay, so it's normalized to a particular unit. Are we doing okay so far with these numbers? Okay. So Pat says, okay, TAC, care for a rematch? I mean, come on, let's do it again. And I said, sure, let's do it. And the next one is 3. Okay. Well, with 3 elements, I can do it in 2 comparisons. Because if you look at an array of 3, okay, like that, I use binary search. This is the first one I compare. After this comparison, I can either have this left or this left. So I have one more comparison to do in order to confirm that all 3 elements are not what I'm looking for. Is that making any sense? Okay. So I'm going to take 2 units of time when the problem size is 3. Pat's computer is going to take 3 units of time, but since that computer is quite a bit faster than mine, I have to remember to divide it by 65536. Now, if you want to say that, but on the average, it's only going to take half of that time because we have a little trick to do even for linear search, fine, we'll divide it by 2. Okay? So Pat's computer in this case will take still a very tiny amount of time to get the problem fixed, to solve the problem. You know what? I'm going to change the format here so we don't use the scientific notation. So we'll go ahead and use a more general number format. And we'll say it's, I think it's 0.00000, something like that. How about that? That's okay. But you can see how little time Pat's computer is taking in order to solve the problem. So Pat is taunting me again and say, "Tac, you want to go for another round? Are you ready for more embarrassment?" Sure, I'm always ready for more embarrassment. Let's make it 7. Now, why am I picking 7? Well, because 7 is going to look like this. I make the first comparison here, and depending on the result of the comparison, I either have the first 3 items left or the bottom 3 items left. I already know how many comparisons it takes to deal with 3, so that's why I pick 7. So in this case, my number is just incrementing by 1. Okay, in this case it's 3. Pat's number is going to be 7 divided by 65336 and then divided by 2. So I'll be a little bit lazy here and just use that as a calculation. Okay, and Pat is saying, I'm winning even more now. If you subtract this number from this number, Pat is actually leading even more now. Okay, so it doesn't seem like I'm working, I'm doing anything to help myself. Okay, and so we'll go with 16 next, because 15 is 7 times 2 plus 1. Okay, so this way I can just say that, well, I just have to add 1 more to the comparison. Pat's computer is going to be proportional to 15. Okay, so it's almost double. But when you look at the delta, Pat is actually even pulling away faster. The time difference is even more. So we'll keep doing this. Okay, 15 times 2 plus 1 is 32. I will need 5 comparison in this case. And Pat's computer is still using a fraction of a second. In fact, it is less than a thousandth of the amount of time of 1 unit of time here. Okay, so we'll keep doing this. And at this point, I'm going to use an equation because I just don't want to have to do it by hand. So whatever is next is this number times 2 plus 1. Okay, so next one is 63. This number is really just this number plus 1. And this number, I have a general equation for that already. So this way I can be, very lazy and just do it this way. And you can see that it doesn't seem like I'm going anywhere, right? I mean, it doesn't seem like I'm, winning with, 8,000 items, not getting there. With, 65,000 items, I'm still not, winning. Doesn't seem like I'm, getting any, advantage whatsoever. But then you say, wow, okay, we're starting to see something here, because when the problem size is about 1 million, it will take me 20 units of time. But Pat's computer or Pat's algorithm is starting to lag behind now. It's taking close to 8 seconds. When the problem size double again, I just have to add 1 more unit of time. But Pat's computer is now doubling the amount of time. So the next one, as you probably would guess, is going to flip. And then at this point, Pat says, it's not fair, Tech. You're using a 486 computer, it's too fast. I need to downgrade your computer to a 386 computer so that it becomes slower. Okay? Well, what is that going to do? It will just prolong the inevitable. Exactly. But why? What is the problem here? The problem has to do with, I know we're running out of time, but I do want to finish this one last part here. If you look at the size of the problem, which is bar A bar in this case, and if you look at the amount of time it takes to solve the problem, the shape of the curve is different. With Pat's algorithm, which is linear search, it's a straight line. Okay. With my algorithm, it is the log of a number. So it looks like this. Okay? By changing the scaling, which is the speed of the processor, this curve, the curve that I use versus the curve that Pat uses, will eventually meet. Okay? It's only a matter of time before my algorithm can beat Pat's algorithm. So this is the important part, because it has nothing to do with how much processing power you're using. It has to do with how efficient is the algorithm that you're using. Okay? So this has everything to do with gaming, because in gaming, what is one of the most important part of gaming? Lag time, right? Okay? And how do you minimize lag time? You make your algorithm efficient. And that's why understanding the efficiency of an algorithm has everything to do with gaming. All right? So I'll see you guys next week. Don't forget you have a homework assignment now. So next Tuesday we can talk about it if you have any questions about it.
And you got the doctor's note, right? You got the doctor's note I sent you?
You are
John Calgill?
Yeah.
Okay,
Yeah,
I just wanted to make sure.
You're fine. You're
Okay.
fine.
I'll make sure I just sign the right spot so that I'll have a sleep when I just
Okay.
That's all right.
And I watched all the videos online, but you never brought up found in the last 2 classes, at least on the videos.
Okay. Yeah, for the last class on Tuesday, I could not upload the one from this class, so you need to watch the one from the 10:30 class.
I did, but you did go over found in that, and then it didn't start till 20 minutes into class.
Oh, okay.
Yeah. So anyway, I was just, so found is just basically a